And we are going to take a look at one of that wasn't even planned. Now my knee hurts a little bit. We are going to... Good morning, fellow mathematicians. Let's start with this. The dogs are staring at me like I'm an alien. Never mind. We're going to take a look at one of Euler's most significant results ever. And it actually pops up in a lot of contexts, in the context of regularization, many analytic number theory stuff, integral evaluation. We are speaking of an infinite series representation. I'm still a bit head hurt. We are talking about an infinite series representation for the Euler-Mascheroni constant. And when I first learned of this, I just thought this was so fantastic. We are going to dive right in. It's a lot of fun. So for this first part, I would like to give you some motivation. So we have the pure definition of the Euler-Mascheroni constant, and I would like to take a look at the asymptotics of the natural log. So I want you guys to notice that the limit as n approaches infinity of the natural log of n plus 1 over the natural log of n is equal to 1. You can also take natural log of n over natural log of n plus 1. It really doesn't quite matter. Oh, I'm still laughing internally about me being this retarded. Now, what does it mean? What do we have here? Well, it just means that natural log of n plus 1 and natural log of n kind of grow at the same rate. And the closer we get to infinity in the argument, the more they grow at the same rate. They are asymptotically equal. Now, why is this important? Well, you can actually prove that there's a whole class of Euler-Mascheroni constants that actually converge to the Euler-Mascheroni constant just at different speeds. This class are just a generalized Euler-Mascheroni constant, Hn, minus the natural log of n plus alpha. Okay, most sources say alpha, and alpha needs to be strictly greater than negative n, because otherwise, well, it would just diverge already in here, okay? Natural log of 0 is undefined, negative infinity. Everything would just explode to infinity. This is a whole class of Euler-Mascheroni constants that converge to the same thing, just at a different pace. Now, I was talking explicitly about natural log of n plus 1, so let's replace the alpha by a 1. Now, this thing converges to the Euler-Mascheroni constant. Those are two equivalent formulations at a different rate, slightly slower maybe, or slightly faster. I believe slightly slower. We are going to manipulate this thing into a summation. We are going to make things harder for us in order for us to make it easier for us, okay, to arrive at what we actually desire. Now, here's some calculations. Natural log of n plus 1. As so always in mathematics, group theory, etc., we would like to add a nice and spicy 0 to this whole thing, something that really does change our natural log of n plus 1. If you only have one apple, that's called natural log of n plus 1, and you don't place any other apple to it, then you still have this one apple ln of n plus 1. We are going to add a 0, but what is a 0 exactly? If you're a smart boy, you might notice that a 0 is nothing but, so let's go with negative, natural log of n plus the natural log of n. Okay, they're just going to cancel each other out. We could add another 0, wouldn't change anything. Why not add the 0 negative ln of n minus 1 plus ln of n minus 1, and so on, up until we reach, I'm going to go with a 0 yet again, natural log of 2 plus natural log of 2. And it really wouldn't hurt us to add yet another 0 to this thing. We are going to call it, we should go with a negative sign, I suppose. Natural log of 1. Natural log of 1 is by definition just 0. Why have I added so much stuff? Okay, why does it make any sense to add so much stuff? Well, to make use of the logarithm rules, of course. Now, we can put this into sum notation, okay, and it's quite clear how the sum has to look. So this is just the summation of, well, those are natural logs of k plus 1 minus the natural log of k. Okay, this is hopefully clear to you guys. But What's with our running index? Well, k is bounded somewhere between 1 is the lowest point that we are going to start at, and well, what should I say, n, okay? It's just bounded between those two. Now by the logarithm rules, natural log of k plus 1 minus the natural log of k is nothing but the natural log of k plus 1 over k is nothing but the natural log, logarithmus naturalis, of 1 plus 1 over k. Okay, so far so good. We can plug this new definition into our optimized, no, not optimized, into our modified Euler-Mascheroni. We shouldn't call it Euler-Mascheroni anymore. This is now Euler-Spirelli. Okay, have you ever eaten Spirelli? Spirelli mit Wurstgulasch. This is quite exciting. Ah, it tastes so good. Wurstgulasch is so good. Oh, Jägerschnitzel. Jägerschnitzel is really good. Never mind with German now. Okay, we are going to draw another beautiful limit. I'm going to denote it as capital L for now. That's the limit as n approaches infinity of, we have our boys, the harmonic numbers, Hn, minus our new definition of this natural log. It's bounded between 1 and n. Maybe you can already see why we did it like this, because the harmonic numbers are defined by the same sum, basically, by the same running index. Pretty gushy, if you ask me. Natural log of 1 plus 1 over k. And now we can continue from this point onwards. So at first I want you guys to notice that they have the same summation, okay, harmonic numbers, and they run over the same running index. So let's bring this running index completely to the front, meaning we are going to end up with the limit as n approaches infinity of, we have the finite boy, where k is bounded between 1 and n, of, okay, this is 1 over k, minus the natural log of 1 plus 1 over k. How should we proceed from this point onwards? Well, Euler was a pretty nifty guy, okay? He was pretty smart and he saw that, well, we can actually get rid of this 1 over k. But how? How can we get rid of the 1 over k? Well, let us think of Taylor series. So if we take a look at the natural log of 1 plus 1 over k, the natural log of 1 plus x, okay? Natural log of 1 plus x can be expressed as a Taylor series by, okay, we have this summation where k is greater or equal to 1. Let us go with r here because we need to make a little change of index. I don't want to use k yet again, which wouldn't make any sense, okay, because we want to plug 1 over k into here later. So not going to confuse anything. So r being greater or equal to 1 of negative 1 to the, now let me see, we have a negative 1 to the r plus 1th power, x to the rth power over r, not k. Now this is what we have at the moment. This converges if our x is strictly less than 1, okay, so the absolute value of our x is strictly less than 1. It also does work when it's exactly equal to 1, actually, but it can't hit negative 1. Okay, take a look at my radius of convergence thing. Does this work? Well, if we were to plug 1 over k into here, 1 over k, it starts at 1 and becomes smaller and smaller, for example, 1/4 overall. Okay, so it's actually in our radius of convergence, and if we were to plug 1 over k into here, we are going to end up with k to the negative rth power. And this is basically it. This is our series representation for the natural log of 1 plus 1 over k. Everything's nicely in the radius of convergence, and we can continue from this point onwards. Now we are going to get the limit as n approaches infinity of our finite boy. K is bounded between 1 and n of 1 over k minus an infinity boy inside another infinity not defined thing, okay? We don't have a gender yet for our limit. It's also kind of an infinity thingy. It's an infinity dog, okay? CJ, my dog. Now, this is r being greater or equal to 1 of negative 1 to the r plus 1th power, k to the negative rth power. I'm going to rewrite it, okay? For reasons that will become apparent in a second. Now we have this. K to the negative rth power is 1 over k to the rth power. Now, if we were to bring the first term to the outside, this is just positive, over 1. Okay, that's just 1 times 1 over k. With this negative sign, it's actually going to cancel out our 1 over k that we have right here. Okay, now the magic is really going to happen. Now what we end up with is the limit as n approaches infinity of this thing, the sum of this infinity boy. Now we can apply the limit as n approaches infinity to here. And what this is basically an interchange of two Lebesgue integrals, basically. Okay, those are just integrals in a higher sense, you could say. They are infinite series. And you can make use of Fubini, for example, or Tonelli. It really depends. You can justify the interchange of limits here. I'm not going to do that because this video is already going on for quite some time and I would like to get to the point. Okay, you can justify it rigorously. Take a look into some analytic number theory book. There's probably some source there. We are going to interchange those two infinity boys to end up with something completely different, kind of. Okay, we are going to have our, also you can bring the -1 into here to -1 to the rth power. We are going to have our infinity boy r being greater or equal to 2 of our new infinity boy k being greater or equal to 1, cray being never mind. So we are going to have -1 to the rth power over r, 1 over k to the rth power. And there's only one thing that you might need to see here. This first term is independent of k, so you can bring it into here. And then we have the infinity boy, where k starts at 1 of 1 over k to the rth power. This is nothing but the Riemann zeta function of r. So overall, everything converges. And yeah, it does converge. I mean, it converges to the Euler-Mascheroni constant. So the only thing it really justifies this interchange of limits that we have right here is that our grand final thing, okay, this is the equal sign, this is the really important part. Euler-Mascheroni constant is thus nothing but our infinity boy, where r starts at 2, of -1 to the rth power over r times Riemann zeta function of r. And this is it. I mean, isn't this kind of fascinating? What we have here is a constant, which is basically an infinite superposition of Riemann zeta functions. And I also think this is quite fascinating because it kind of looks to me like a Dirichlet-L series. You can express each and every convergent Dirichlet-L series as a superposition of Hurwitz zeta functions. And well, Hurwitz zeta functions are just a generalization of our Riemann zeta function. So there are quite some similarities and I just think that this result is extremely beautiful. If you didn't understand everything I did here, just go through the calculations again, take a piece of paper, try it out for yourself. But other than that, it's a really nice result of analytic number theory. And I'm so proud to be able to present it here on my channel. Thanks for watching. If you enjoyed this video, please like, subscribe and recommend channel. If you want to support the channel a bit more, buy those t-shirts I created, especially the new merch. We also have logo merch out there. I'm still waiting for the delivery with the new logo merch. Check it out, it's pretty amazing. Yeah, you can support the channel extremely this way. And well, what should I say? Thanks for watching. Up until the next video, have a flammable day and I hope I'm not going to trip over yet again while walking out of the room. Ciao.